Okay, Yunfei, yeah. Let's continue the discussion. So what we talk about is from a single electron to more complex one, right? That part, do you understand? So as long as we know where the electron clouds within distribution, the distribution within any given shape, we can compute. Use a computer to describe any scattering pattern with this very simple equation. And this equation basically says your form factor comes from a Fourier transform of electron clouds. In a nanoparticle, we assume electron clouds is from the center to the outside diameter r is the same as given by rho electron density. So you basically do a Fourier transform of a constant electron density, pretty much like this slide. Constant electron density. If you do a Fourier transform, this is what the shape you should look at. Then what detector measures is this amplitude square. So if you cover the negative part, because we cannot measure, so that is pretty much the scattering shape we actually see. Okay? Ben?
Yeah, so just so I understand this conception, real space is representative of the X-ray hitting the sample, and then the inverse space is the signal we get out, the scattering signal that we relate to a frequency.
Yes, yes. Okay, that's perfect. I would add on a little bit in the real space. It's not just the X-ray hit, it's just your material naturally presents in a real world, okay? Where we are now, like. Your atom has more atoms within it, has pattern a certain shape or structure. That's what it is seeing.
So it's an average of that signal?
Yeah. Yes.
Yeah. Okay. I just want to make sure.
So I want to talk about challenges in scattering. So in principle, using the Fourier transform, you can jump back and forth between the real and inverse. That's a superpower. I wish I could have it. But within that ability, as long as you measure the scattering profile, you can do an inverse Fourier transform to get electron density map of your molecule, right? You can do forward, you can jump back from inverse. So in principle, if you collect a scattering pattern of a given structure, we should know exactly which each electron resides within that molecule. Conceptually, okay? Because what we did forward, we jumping from real space to inverse space is we did a Fourier transform so that we see where each electron will contribute to scattering signal. Now, it's possible to go back from scattering signal to where each electrons are. Only caveat that we can fully resolve is a paradox called phase problem. PHASE, phase problem. And what is phase problem? It's a very interesting question. Let me explain. The phase is basically your electrons, your magnetic waves, the scattering signal is always a wave, right? We basically cannot see two things at the same time. We cannot see the intensity and the phase at the time or phase. What detector only measures is amplitude of your intensity, which is shown by here. It just inherently limits. So when we measure the X-ray, we lose the phase angle. So that phase angle is gone. What that means, I'll show another example. So if you can see what the difference between this one versus next one is, you shifted by a phase angle by a certain degree, right? But when X-ray pick up, it only measures what's the highest point to the lowest point. So intensity will be, let's call it E0. It will be E0 squared. So when you take a square turn, you lose this phase angle. So this one will look exactly that one. So conceptually, you can do inverse Fourier transform to see any shape of your structure, but unfortunately, because of phase problem, we lose the ability to track exactly locations. What is the physical meaning, or why we should care about this phase problem is we lose some structure information within our material. So in order to fully construct your 3D location of each element, you need to use some more complex techniques. Something that is being developed in latest synchrotron is called coherent scaling. So if you use coherent X-ray beam, you can do tachography, then you can fully see what is three-dimensional space of any material. Okay, you don't lose any single information. You can address this phase problem. Okay, so fully transform. I'll show one more example in the next class. There is a cool video. I'll post it. So someone wrote a software can do real Fourier transform of any given geometry. So if you watch the videos, you will be able to see how a dot is Fourier transform will look like, how a square will look like. So that's basically gives you all the signal. Let me see if I can find it now, if I have time. But let me first disconnect to make sure I got the right one. If I can find it, then let's take a look. That helps everybody to understand.
There's a similar app where you can actually just take a picture and you'll just do the Fourier transform of whatever you took a picture of.
Yeah. Okay, I think I found it. So this particular person,
Gentlemen,
Dr. Paul.
techniques like X-ray scattering.
Can everybody see it? Let me first pause, and I really admire this person. He is a very good explainer for scattering. He runs a small X-ray beam labs at Japan for a couple of years, and now he is back into Germany running another similar lab-based X-ray source. So he has some really cool demonstrations. So let's watch it together. It's only just 5 minutes, and show you what I mean by real-time Fourier transform.
And X-ray diffraction can somehow probe the structure that we have inside the material. However, it is often difficult to understand the patterns that we see in these experiments. It turns out that the patterns that we see in these experiments can be calculated as the Fourier transform of the structure in the material. To make this easier to understand, we can play around with images. I can show you what a Fourier transform looks like for a given structure by transforming the images of this camera. And here we are. You will notice that I've turned this image black and white, and the image on this side shows us the Fourier transform of the camera image. Mm-hmm. Now, I should explain that I have done this demonstration before, and you can actually find it on YouTube. So if you've seen it before, don't bother with watching this one, because it's pretty much the same demonstration. So let's begin. The most simple structure is a single sphere in a solution. You will see that the scattering pattern of that consists of an oscillating function. Due to Bernoulli's principle, I cannot tell whether it's a white sphere on a black background or a black sphere on a white background, which is commonly referred to as the phase problem in both scattering and diffraction. You see that the patterns are the same. In scattering, the larger the structure, the smaller the features. So here we see the structure of a very large sphere. You see that if I take it back a little bit, that the spacing between these oscillations increases. So the larger the structure, the tighter the angles. Anisotropic structures like cubes and ellipsoids will also show you an anisotropic scattering pattern. Here we see ellipsoids, and you see that these patterns actually rotate together with the structure. So when you Fourier transform, or when you do a scattering experiment, the only thing that remains conceptually easy is that all the angles, all the rotations are exactly the same. Now, if I have a solution of structures, say spheres, you will see that if the solution is monodisperse, that the oscillations still persist. However, if I have a polydisperse structure, you will see that the oscillations disappear, because we're now seeing a superposition of the Fourier transforms of each of these structures, more or less. But of course, for polydisperse aligned structures, we see something like this. So we see a smeared out pattern, but you can still see that it's anisotropic, because if we rotate it, you see the main feature rotate together. Now to the diffraction examples. I have here a grid of points. You will see that we now see the diffraction spots appear on the Fourier transform. And if I increase the spacing between the points, you'll see that the Fourier transform spacing reduces. Likewise, if I decrease the spacing between these points, simply by moving this further away from the camera, the spacing between the points in Fourier transform increase. Similarly, we can do grids, in which case you see a nice sort of kaleidoscopic effect of the grids. There's one more feature to this Fourier transform, which I can switch on in a moment. This is actually more of a gimmick rather than a feature. I can do the Fourier transforms in color. I still don't know whether it's going to be of any use, but you can show, for example, the interference pattern of spheres of different sizes with different colors. You see that each color has its own interference pattern because the sizes are different. Or you can show the Fourier transform of different shapes, each with its own distinct color. As I said, just a gimmick, but it's nice to know that you can do things in color sometimes. Now, if you like a copy of this program, you can. It is
Okay, I'll post exactly the same link so that you guys can view it again if you want. So let's come back to, as you can see, in the demonstration is actually a good explanation to what we have seen today. What you do in scattering is a fully transforming electron density within any structure. And if you recall, before he put something in there, it's just a picture of himself. There's a Fourier transform image as well. In principle, all the shape of his beard, his eye is encoded there. It's just a little bit harder to model to do back calculation. But in principle, you can. If you take a picture of myself, you can get the shape of me. It's just more complex than typically the simple Sophia pattern you guys see, because it gives you very simple interference pattern like a rings. So with that, I want to finish this class, and I want to give everybody plenty of time to review the video and textbook on this important part, how Fourier transform works between a real space object to what you see in the scattering. This is going to be the most challenging part of this lecture. If you can comprehend this concept, the rest of the example is very easy. So in this Thursday, let's do a Q&A session for the class. And we can go through it one more time if anyone have any question regarding this part, because this is most important in probably this whole lecture. Understand the Fourier transform, how electron density distribution within any object with respect to scattering pattern. Okay? So let's do that, and let's meet again this Thursday, but I'll use the opportunity to answer any questions or chat any topic if you like. Any question then for today's class? If not, anyone? Any more questions? If not, then let's finish today's class. Let's come back again on this Thursday. Okay?